Hello and welcome to this lecture. In this lecture, we are going to look at a limit of a function at infinity. Okay, what is this definition? It's again very simple. We'll again use the same old definition of a limit. What is limit at infinity of a function? For every sequence an with an tending to infinity. You've been looking at this an diverging off to infinity, right? It's growing unbounded to infinity. The sequence f of an should converge to some L. If that happens, then we use this notation saying limit as extending to infinity of f of x equals L. Okay, so notice what's going on. For every sequence an which is blowing up, if you hit it with f, you should go to some L. If that were to happen, then you say that limit as extending to infinity of f of x is equal to that particular value L. Is that okay? So there is no other notion here. With this, we define limit at infinity. A natural definition, right? As x grows to very, very large values, what value does f of x go to? Okay, so this is a way in which you formally define that limit. What about tending to minus infinity? You don't have to do something similar. You could do something similar, but you don't need to do it, because the reason is limit as extending to minus infinity of f of x is the same as limit as extending to infinity of f of minus x, right? I can do this. I can flip the function. Instead of asking what happens to the function as it extends to minus infinity, and plus infinity is here, minus infinity is here. Instead of asking minus infinity, I'll flip the function around. I'll make it f of minus x. Then my what went to minus infinity is going to plus infinity now, right? So that's enough here. So extending to infinity alone is enough. You, instead of f of x, you do f of minus x if you are interested in x equal extending to minus infinity. Is that okay? So extending to infinity alone is a decent enough notation as it is. Infinity alone is enough. Why worry about minus infinity, right? So we'll just change the function around and worry only about infinity. Okay, so here are some basic limits. These limits are important to know, and we can use these over and over again. So once we have these basic limits, we can use them in our combining rule, as long as we don't run into some infinity minus infinity 0 times infinity problem. We are okay, right? So we can do that in a very interesting way. Constant function, of course, in the asymptote as extends to infinity, asymptotically it's constant. X asymptotically diverges to plus infinity. 1 by x asymptotically converges to 0, right? So these are very basic things, quite easy to establish. Using these definitions, you can very easily do this. Okay. Now, when you have the power and the exponentiation also, this works out quite easily. If you look at any a which is positive, okay, x power a as a x tends to infinity in the asymptote, for any positive a, x power a will go off to infinity. This a could be very small, 0.1, 0.001, doesn't matter. The power is powerful enough. X power a will go to infinity. Of course, if a is 1, you fall back here. If a is 2, you get the quadratic x squared. A is 3, you have x cube and all that. For large values of a, you clearly see that this x power a, for large values of x, it will blow up. But even for very small values of a, as long as a is positive, x power a will blow off to infinity. Now, x power minus a on the other hand will go to 0. Okay, so this is going to infinity 1 by that, right? This is x power minus a is 1 by x power a, and that will go to 0. So it's like x power a, 1 by x power a, this goes to infinity and 0, just like these guys go to 0. Okay. Now, if this is for power, okay, hope power is clear. It's very easy. You may ask, why don't we do a less than 0? But minus a is covered here, right? So this is covered here, so we are okay. Now 0. Now we move to the exponentiation function, right? What happens to a power x as x goes to infinity? Now here it depends on whether a is between 0 and 1 or a is greater than 1. You remember those plots that we made for the exponential function? When a is greater than 1, it had this shape. When a is less than 1, it had that shape, right? It was like the ulta shape. Okay, so you have to be very careful about that. So if a is between 0 and 1, a power x as x tends to infinity will be 0, and a power minus x will be infinity. Okay, but if on the other hand a is greater than 1, a power x will be infinity, a power minus x will be 0. Okay, so these are easy to remember. Supposing you put 2 as a as 10 or something, 10 power x as x tends to infinity is infinity, 10 power minus x as x tends to infinity is 0. It just falls off to 0, just does the other plot. Okay, so these are our basic limits. Once we have our basic limits, we use our rules to combine them to figure out the limit for any other function. Of course, you have to watch out for infinity minus infinity and 0 into infinity. That will always be a problem, it will always be there, you can't do anything about it. But when you run into that problem, you look at it closely, that's all. Otherwise, you can use these limits happily to figure out limits at infinity, the asymptotic values taken by the function. Like I mentioned once again, these things are very important in electronic circuits in particular. So, where does the voltage settle down? And this may not be infinity, we may use infinity in the theoretical calculation. In practice, it may be like a few seconds, it may settle down very quickly to that value. Okay. So, here are examples. Let us go ahead, find limits. So, these are very reminiscent of sequence examples we saw before. You can go back and look at the sequence examples we saw, very similar. I am doing something similar here. Let us start with some simple ones. Here is x tending to infinity, 2 plus 3x, 3 plus 5x. Okay. So, it is going to infinity by infinity type thing if you just substitute, but you should not do that. What should you do here? You have to divide by x, right. If you remember 2 plus 3n by 3 plus 5n, that is what we did. No, we divide by x. Divide by x, you get 2 by x plus 3, that has a limit of 3. 3 by x plus 5, that has a limit of 5. So, this will go to 3 by 5. Okay. Another way to think about these kind of things is 3x is very large compared to 2 for x large, right. So, this is almost like 3x by 5x, x will cancel, it becomes 3 by 5. Okay. But formally, the way you do it is what I said. Okay. So, you divide by x and then take the limit in the numerator denominator, you have 1 by x going to 0. So, you get 3 by 5. Is that okay? Hopefully, you got that. So, next one here is also very similar, except that x squared is here, x is here, you divide by x squared, numerator will go off to 0, denominator will be something else as x tends to infinity, some constant. So, this guy will be 0. Okay. So, it is very similar to n tending to infinity. Okay. Very similar arguments you make here. Another way to see it, like I said, is 7x squared dominates here, 3x dominates here, x and x will cancel. So, you get 3 by 7x. Okay, and then x extends to infinity, that goes to 0. That is also possible, right. Okay. And here is 1 by x minus 1 by x minus 1. I'll leave you deal with this. This is quite easy. Again, you can convert it into a polynomial and do it, or you can tend x to infinity. This is 0 minus 0. So, you'll get 0 here as well directly. Okay. What are the other problems? Let's come to this one. This one is interesting. Okay. Look at this one here. So, it says 1 minus 2 power minus 3x. Okay. What is 2 power minus 3? It is 1 by 8, right. So, this is 1 minus 1 by 8 whole thing to the power x. What is 1 by 8? 1 by 8 is less than 1. Okay. So, you go to your basic limits. If a is less than 1, a power x as x tends to infinity goes to 0. So, this part goes to 0. As x tends to infinity, 1 minus 2 power minus 3x tends to 1. Okay. So, this goes to 0. This 1 stays by itself. It is constant function. Okay. So, this goes to 0. So, this 2 power minus 3x. So, expressions of this form often occur in electrical systems. Okay. So, this is very important to know. This 2 might be E or something you might have seen, but anyway, this is very important to know this kind of function. So, what about these guys? These guys are also very easy. 0.5 par x, 0.7 par x, asymptotically 0, 0. So, this is 1 by 2. Okay. This one, asymptotically, it's going to be 2 par x. So, look at how quickly you can do it. I mean, you don't have to remember all these rules and all that. Once you get the sense of what's going on, it's very easy. 2 par x by 3 par x, it's like 2 by 3 whole power x here, right. So, and that will go off to 0, right. You can divide throughout by 3 par x. So, you see that this 2 by 3 power x is 2 by 3 is less than 1. So, this will go off to 0. So, again, this limit is 0. This limit is also 0, right. 1 by 2 par x plus 3. You can divide throughout by 2 par x and you will get all less than 1 raised to the par x, right. So, this will go to 0. X par a minus x par b. We did n par a minus n par b, if you remember. So, everything depends on whether a is greater or b is greater. If a is greater, you pull x par a out, okay, and then you will get 1 minus x power b minus a, and then you argue what's going to happen. Yeah, so you will get 1 by x power some positive thing or x, and depending on that. So, it may either go to plus infinity or minus infinity, depending on whether a is greater than b or a is less than b. What about here 1 plus x par a by 1 minus x par b? Okay, again, it depends on whether a is greater or b is greater, or they could be equal. If they are equal, then it will go to a constant, but if they are not equal, then it may blow up to, and depends again, if a is greater, then this x par a will dominate and it will take it to very large values. b is greater, this will pull it down to 0. Okay. So, these are cases you have to argue and carefully do. So, once again, for different forms, rational forms, exponent form and all that, you should be able to easily see what happens to asymptotic values. When x becomes very large, what happens to these functions? So, that is where limit at infinity comes and helps you. Okay. So, let me summarize. So, this is a summary for this entire sequences, limits, continuity type module that we did here. Okay. We started with sequences and limits, just sequences of real numbers. We looked at very interesting things that you can do with powerfully with sequences of rational numbers, right? You got very new numbers with sequences and we could compute functions with them. All of that was very, very powerful. Not only that, when a function f acts on a sequence that has a limit, you get this notion of limit of a function, and that's very, very useful in defining continuity. We'll use this limit of a function more in future classes in calculus to define something called derivative. So, that's very, very powerful. Okay. It's got huge applications. It will solve all the other problems that we want to do, and then also integral calculus we will use. So, this limit of a function is a very, very crucial idea, and it comes very neatly because of sequences. And of course, here we saw continuity. Okay. The important skill you should pick up in this module is how to compute limits for sequences and functions. Given a limit, given a sequence, given a function, how do you understand its limits? How do you compute them? Okay. So, we have seen numerous techniques for it, numerous examples. All of that should do, but if you can see more techniques, if you can learn more techniques on your own, that's great. Okay. And try to do practice, a lot of assignment questions, practice assignments, a lot of books. The books that we mentioned are also useful. Thomas's Calculus is a very useful book. It's got lots of problems. You can pick up all those problems and do them. So, a couple of topics I've omitted, lots of topics I've omitted also. Okay. One thing I've omitted is the epsilon delta definition for limit of a function. It's very popular. It's sort of analytic. It's a little bit more important for proving and all that. I've omitted that. Of course, I've omitted proofs. Okay. I'm not entirely happy that I omitted the proofs, but for a course of this nature, the proofs are not central. They're a bit distracting sometimes. So, if we find time, we will give you some proofs for some of the more difficult ideas that we saw in this course. Okay. So, this concludes this limits, sequences and continuity section of this course. I hope you enjoyed it. Thank you very much. Bye-bye.